Yeah. Thank you for the invitation. It's a pleasure to speak here. So, right, let me write my title again. It's Homotopy group quotients of DG categories and skew group algebras. So, this will also be the content. The content of the talk will be. So we are first. So what's the plan? I'll first recall. We'll have two recollections. So the skew group algebra, what is it? If you have an algebra and an action by a group on an algebra on this algebra, then you can define the so-called skew group algebra, which is a generalization of the group algebra, and it's a standard construction. I think many of you will have seen it before. Let's remind everyone how this works. It's not too hard. So skew group algebra. And then the other thing I want, or what I want to connect this with is well, say you have a DG category and a group acting on it, and then you can take the so-called homotopy group quotient, and I'll kind of explain to you what I mean by that. I think also a standard notion, so you won't be surprised, but definitely good to specify what I mean, and then we'll have the main result, which will connect these two things. It will basically be saying that this Q group algebra is a way to compute the homotopy group quotient up to Morita equivalence. And so connect the two. Connect the two above. And then we'll kind of explain a little bit how you prove these things. And for that, we need to use infinity categorical technology.
Can you write a little bit bigger, just a little
Oh,
bit?
yeah, right. Yeah, sorry, my screen is quite big. So we're like, well, yeah. Sorry, I'll write bigger. Thank you. So, so the group action, we'll look at how to describe group actions using infinity categorical module actions or modules, module structures, one should say, and using these some abstract infinity tools, we'll then be able to prove, which I'll explain in part 3. We'll then be able to kind of sketch the proof, and then lastly, I'll look at some consequences. We'll look at some consequences of the result, and let me also mention that this is based on a preprint, based on archive preprint. You can find well, let me put here the number, 2501, sorry, 250-13666. Okay. 3666. Okay. Right. So to get to the actual talk, let us fix for once and for all a group, fix G as a group. And it's not necessarily finite. Necessarily finite. I promise to write bigger. Please remind me if I stop doing this. So K is any field. And notice that we don't require the characteristic of the field to match the group order, or like not match. We can have any characteristic. Everything I'll be able to explain will be independent of the characteristic. So we have this, and then let's say A is a K algebra. This is a K algebra or a DG algebra, also with the field K. And let's say G acts on A by automorphisms. Then we have a definition of the skew group algebra. So the skew group, possibly DG algebra, A star G, has as underlying, so it's a DG algebra with a vector space and a graded vector space and a differential graded vector space and a multiplication. So as underlying differential graded vector space, just simply the coproduct. you take a coproduct G, which is, you can write it as follows. It's a G full, so you take all elements of the group, and then you take an entry indexed, so G times A entry indexed by G. So this would be elements, we label elements are labeled by pairs G comma A. And you want to do that so that you can, we will only need this label to define, I should go into full screen mode. We only need that label to define the multiplication, and then we won't need the notation afterwards anymore. So how do you, I have these Zoom pop-ups everywhere, and I need to move them on my screen. Okay. So the multiplication, so we have a differential graded vector space. We also need a multiplication. So we define multiplication on the generators, right? Every element is a sum of such pairs, G comma A, and I'm just going to tell you how to multiply two elements, and then you would linearly extend this to get the multiplication determined by you take G1 comma A1 multiplied with G2 comma A2. This is defined by you multiply G1 and G2, and then you take A1 times G1 acting on A2. So this is the G action. And yeah, that's simple enough. And you can check that this defines the DG algebra. And let's have some examples. Example 1 would be that if you choose A equal to K with the trivial G action, then the skew group algebra is simply the group ring. Example 2, less slightly more less general and more specific example where something happens. So to take the path algebra of the A5 quiver. So I have to also tell you the orientation of the A5 quiver. So we'll orient A5 like this. And then you have an action of Z2. This acts by transposition, by reflection. So what is it along the horizontal axis? You reflect, and so then you can compute the skew group algebra. So A star Z mod 2Z, this will be equivalent. So I won't tell you exactly the algebra it is because, well, let me first tell you what it is Morita equivalent to, and then explain why I don't tell you the entire algebra. So it's Morita equivalent to the path algebra path algebra is even quasi-equivalent if you want. Yeah, maybe this is a good explanation. Quasi-equivalent to the path algebra of the quiver with 3 vertices. So what happens is the group at the reflection, it identifies these 2 vertices, and on this, the third vertex, because it's a fixed point, you have to basically add a copy of the group algebra of Z2. So you add a loop epsilon, modulo epsilon squared is equal to 1. And then it's only quasi-equivalent, not equivalent, because in the skew group algebra, basically what you're doing is you have 2 copies of these 2 vertices. So if this is 1 and this is 1 prime, then they give you a single object 1 here in this path algebra, but they give you 2 objects in or 2 idempotencies if you want in the skew group algebra, and of course the corresponding modules, they would be equivalent, but you have a degeneracy there, or like a unnecessary redundancy is a better word. You have a redundancy there, which is why the skew group algebra is kind of bigger than necessary, and this would kind of be the smallest possible way to express it. And then if your characteristic of the field is not equal to 2, then this is the path algebra of D4. D4 is this corner. Right. And yeah, this is a fun example. We see that kind of some of these, well, the definition of the skew algebra doesn't depend on the characteristic, but if you want to compute it, sometimes the behavior changes, of course, depending on the characteristic. And what we see here is that the derived category of the skew group algebra, this is more interesting. Than just looking at the derived category of the group of the quotient algebra, DT algebra, right? If you took the quotient, this would just be A3. And okay, well, at least A3 is somehow, the representation theory of that is easier than D4. So in this sense, it's more interesting. So this is why in the literature on say finite dimensional representation theory, whenever you have a group acting on some algebra or DG algebra, passing to this Q group algebra has become one of the standard constructions to study somehow equivariant representations or something like this, or well, let's say representations in the presence of a group action. And there's a more general version, version of the construction, replacing so a DG algebra or for a DG category. And what you have to do, you apply the formula for this Q group algebra Hom-wise. So basically to every Hom, you add a G-fold product of Homs twisted by the action of the group, and then multiplication also is twisted. And this is how you can define a version of the Q group DG category, which in the case of the DG category as a single object reduces to the previous construction. If you want to have the precise formula, you can go to my paper, but I think it's kind of, if you think about it for a few minutes, it won't be difficult for you to come up with the correct formula. So this is all you need to know for the moment about skew group algebras and skew group categories. Let's now look at homotopy group quotients. So how this works is, let's say A is a strict G action. There are also non-strict ones. We'll only be looking at strict ones for now. So a G action on a DG category C. If you have such an action, this can be identified. Sorry, not can be identified with a functor from. I'll explain this now. So from BG to DG cat K, where BG, this is the category with a single object and automorphisms G and G. So category with single object and the Hom in BG from the single object, and the single object is just the group G, with composition being multiplication in the group. And so if you have such a functor, this functor will map the point to some DG category, let's say A, and then it will map each element G acting on this to the action of G, giving you an automorphism of A. So you can go back between functors out of BG to DG cat and G actions. It's kind of the same datum. There's no loss of information in either direction. And so if you have such a functor, you can take the homotopy group quotient. So the homotopy group quotient, this would be the homotopy is defined as the homotopy colimit colimit column over BG, let's call this functor row of row in ggcat. Of course, the homotopy colimit is, so I have to tell you homotopy colimit with respect to which model structure. So this is with respect to the Morita model structure. And here the weak equivalences in the Morita model structure are the Morita equivalences. Weak equivalences are the Morita equivalences. And I don't want to define Morita equivalence here directly, but just to give you a brief idea what it is. So basically it means that the perfect DG category of perfect DG modules is over, say, A would be equivalent to perfect DG modules over B. Then A and B are Morita equivalent. And Morita equivalence is a teaching functor that induces such an equivalence. Okay. So this is, of course, the homotopy colimit it's a homotopy colimit, but it's in the model categorical sense. So it's not determined uniquely, but it's then determined up to Morita equivalence. And this is what you could call the this is the somehow categorically the correct notion of group quotient, or the homotopic notion of group quotient. And there's also an infinity version. So infinity version, or infinity categorical group quotient, where which works as follows. So you would take the so we will need this in a bit, or in a second. So you first look at linear categories over K, so linear infinity categories. This is defined as modules over D of K in presentable left stable. So what does all of this mean? So first of all, those are stable presentable infinity categories. So stable is just a version of triangulated. Presentable just means large in some sense. And D of K here is the symmetric monoidal infinity category. And then you would look at modules over that, meaning that you have a tensoring. You left tensored by D of K, or D of K acts on your presentable category, and then you call that linear. And so there's a functor. If you only know about DG categories, what you need to know is that there's a functor from DG cat, okay, that more precisely the nerf to linear categories over K. And this would map a DG category A to the intercompletion of the DG nerf of perf of A. So, and this is called the derived infinity category of A. Derived infinity category. And then the infinity categorical group quotient. So infinity categorical group quotient, we will denote it by dA sub G. This is defined as the colimit of the functor from, you go from BG to, or let's say, the nerf of BG, you go to the nerf of DG cat via the nerf of rho, and then you go to lin cat via the above map, and you just take the infinity categorical colimit of this. And so how does that relate with the previous notion of homotopy quotient? So this functor has the property that it maps homotopy colimits to infinity colimits. More precisely, it would map homotopy colimit cones to infinity categorical colimit cones. And hence, this is equivalent to the derived category of the homotopy colimit. So we can, what is the upshot of this? you can look at the homotopy group quotient in DG land, or you can look at the infinity group quotient, and you can go between them back and forth interchangeably. Somehow both essentially compute with the same thing, except for going from DG categories to K-linear stable infinity categories. But you can go back in this functor. So this functor is induces an equivalence on certain categories. I don't want to go into that detail, but so you can not only go in one direction, you can also go back. So let me state the main theorem. So let's say rho from BG to DG cat K is a G action on a DG category A. Then the homotopy colimit of rho is Morita equivalent. To the skew group DG category, so A star G. And so this somehow gives a universal property to the skew group algebra, skew group DG category, which kind of explains why, if you want from a conceptualist viewpoint, why this is the correct construction, and somehow why one should really be looking at it instead of just somehow phenomenological evidence that it's the correct construction. So, and the remark, so equivalently, we will prove, and we can and can prove that the infinity categorical group quotient, which is the this guy, is equivalent to the derived category of the skew group DG category. Equivalently can prove that. And second remark, again, let me say that the theorem, we need no assumptions on the characteristic of K in the theorem. And this is insofar remarkable that most of the literature on skew algebras, whenever they prove that it's equivalent to another construction, it typically only works for in good characteristic. I'll also come back to that later. So now we're kind of able to state the theorem in somehow. I mean, the theorem itself, you only need to know what a DG category is and the model know about the model structure on DG categories. But for the proof now that at least I only know like that the best proof I know uses higher category theory, so infinity category theory, and so I will try to explain this now. So the categorical, and this will use the categorical group algebra. So what is that? So the categorical group algebra. Let's first look at spaces. So spaces is let S be the symmetric monoidal infinity category of spaces. So spaces just means topological spaces up to homotopy equivalence, if you want. And then there is a symmetric monoidal functor. Symmetric monoidal functor from spaces into linear categories. Over K. And this functor, let's denote it by D of K coproduct blank. So what it maps to, if you have a space, it would map the space to the colimit over the space of the constant diagram with D of K. So all we will need is that it maps G to D of K coproduct of G, which by the way is equivalent to D of K product of G. So limits in this limit and this colimit are equivalent by presentability. So if you want, it's the default product category. And so why do we need that it's a symmetric monodal functor? Why did I mention this? So somehow G as a group defines an algebra object. In the symmetric monoidal category, spaces, and since this functor is symmetric monoidal, it maps algebra objects to algebra objects. Thus, this categorical, this DK coproduct G is what's an algebra object in lincat K. This is a monoidal infinity category. Monoidal K linear infinity category. And this is somehow very elaborate language to say something very simple. I mean, how does the monoidal structure look like? Or, I mean, yeah, in infinity land, you can never just say, well, you can rarely say just what the monoidal structure is. But we can unravel it more now on objects, what it does. But you couldn't just construct it by specifying a formula on objects. That's what I want to say. So let's say we have an object, coproduct over G in G of xg, and coproduct G is in G yg in D of K coproduct G, right? We can, our objects, if we can think of them as G index tuples. So I'm writing this as such a coproduct, where xg just lives in the G index component in this coproduct. For this, we have that the coproduct G and G xg tensor the coproduct, let's say H1, H1, H2 in G, YH2. This is equivalent to the coproduct of G and G. So this would be the entry in the G, the entry in the G indexed component. And then you take the coproduct over all expressions of G as the product of H1 and H2. And you take X H1 tensor X H2, where this tensor product is in D of K. So what it is, you just have a G-indexed family of copies of D of K twice, and the tensor product just shuffles the indexes around according to the product to the multiplication in the group, and this is then extended linearly. Right, so this is the monoidal structure. It's kind of an obvious monoidal structure if you want. And so why this is relevant is the following. This is a theorem that I learned from a paper of Haneli, Knossen, Ramsey, and Janowski. Though I think they also cite other papers for the result. I'm not sure what's the first reference exactly. So so functors, I should learn it from them. So functors out of from BG, or let's say the nerve of BG to be precise, to lincat K. This is equivalent to categories which are linear over over this monoidal category. So by this I mean modules over D of K coproduct G in say left modules in presentable left stable. So this means and then this theorem is not literally true. The way I stated it is you need to add so modulo size issues. This has something to do with the regular cardinals and well, yeah, so, essentially set theoretic size issues. So I'll ignore that question. If you want a precise set theoretic discussion, you can go to the paper. But let's just take this theorem as true. So what does any of this mean? So or what does the side here mean? So these are left. So this is now an element in here. is presentable. So objects are presentable, stable infinity categories with the left tensoring. So left action or tensoring by dk coproduct G. So this would be, say you have, if your category is called C, then you have a map from D of K coproduct G times C to C, plus all the homotopy coherent data exhibiting somehow this is an infinity categorical model structure. And why is this this theorem kind of interesting to us? So this allows us to now treat group actions in terms of module structures. And so in higher algebra, Lurie develops a robust framework of module, so I'll say actions, say module structures. For instance, you can tensor when you have a bimodule and so on. And we can use this. So this is like, we can use this to, yeah, if you want to compute the infinity group quotient. So a priori, somehow from the definition, it's very difficult to approach the study of the infinity categorical group quotient, at least from my perspective. I somehow wasn't really able to make sense of it. But this theorem allows you to translate that study of this co-limit over BG into algebraic questions. And so for this is now how now what I want to explain how exactly this works. And so let's look at the adjunction, or look at the adjunction. Consider the adjunction. So psi is defined the functor. It's the g-fold product over the identity of on d of k. This is a functor going from the dk coproduct g to d of k. Maybe one thing I forgot to say. So well, yeah, before I tell you about the right adjoint, maybe one more comment. So d of dk of g is called the categorical group algebra, called the categorical group algebra, and as in the title. And you can think about it as being like the group algebra, except one categorical level higher. You don't form the group algebra with respect to an algebra, but you form it with respect to a category, a monoidal category. Yeah, it's a symmetric monoidal category. And then, so just to explain why this was the title of the section, is because this is the name of this monoidal category. So you have this adjunction. What is the right adjoint? The right adjoint is simply the diagonal functor. Diagonal functor. And so if you now have, let's say, G acting on D of A, again, let's say A is a DG category, G was acting on the DG category, then you got an action of G on the derived category of A. By the above theorem, I now get a I get a module structure, so I can tensor with D of A as a module over D of K coproduct G blank, and from this I get a new adjunction. Get adjunction or have a junction. So on the left side, you would have d of a, which is equivalent to d of a tensored over d of k coproduct g with d of k coproduct g. Right? These are all categorical tensor products, but they work the same way as, say, tensor products of normal modules. So if you tensor, so if you tensor a module over the algebra with the algebra, you just get back the module, right? So this is the left side of the junction, and the right side is d of a tensored d of k, the categorical group algebra, d of k. So, and then let's call this functor f and this functor g. Now, maybe a proposition about this, why this proposition, why this adjunction is interesting. So first, I don't know if you guessed it, but if you, in the right-hand side, d of a tensor d of k coproduct g, d of k is, this is equivalent to d of a g. Is equivalent to the, is the infinity categorical group quotient. So this proposition tells you that you can compute the group quotient as this infinity categorical tensor product. This in and of itself isn't helpful yet. What is helpful is this adjunction. So before that, maybe just one comment, the functor f, or let's maybe say more about the functor f. F is the morphism, the functor, or is equivalent to the functor, is equivalent to the functor from the infinity categorical colimit cone. Categorical colimit cone over Bt, under Bt. So yeah, you have this colimit cone under Bg, and if you evaluate that, and this gives you a functor from d of a to d of to the infinity categorical group quotient. This is just the functor in the cone, and this functor you can identify with f.
Can I ask a question?
Yes, please.
So maybe I'm misunderstanding proposition 1 here. Can I just read it as a triangle equivalence, or will I be missing some information? Or the
As what equivalence?
as a triangle equivalence?
Yeah, well, it's an equivalence of infinity categories. In particular, when you go to the homotopy category,
Yeah, they're
both of
stable,
them
right?
would be stable. It would be an equivalence of triangulated categories. Absolutely.
No, what I'm saying, can I just read it as a equivalence of stable categories, or will I be losing some information?
You mean without the k-linear structure?
Uh-huh.
I mean, maybe you want your triangulated category to be k-linear, and then you would have to. But you can just think about it as an equivalence of infinity categories. I think. I mean, we do care about the k-linear structure, right? Because this allows us to talk about that this is equivalent to being enriched in k-linearly, meaning you're mapping objects. They are now chain complexes instead of just spaces. And then we want to compute those chain complexes.
Yeah.
So this is why it's kind of relevant to have this equivalence. So this is an equivalence in lincat k, and it's helpful to have it as an equivalence in lincat k.
Okay, thank you.
I hope that makes sense.
Yeah.
Okay, thanks. So now comes the real helpful statement with which we can compute things. So if you compute this endo functor gf, this is given, so this is a functor from d of a to d of a. This is equivalent to taking the coproduct of g and g, and you act by g. So this is just the g action. By g and g. right? Every element of the group defines an automorphism, and you just take the coproduct over all of these automorphisms, and this is the end of functor GF. So in particular, we can now compute our first thing about the infinity categorical group quotient. If you take x and y in D of A, then now this is where we need the Killinger structure. So the morphism object from f of x, f of y. This is the K-linear morphism object, and it lives inside of D of K. So it's not just a space; it's a chain complex. If you want, you can forget that it was a chain complex, and then it would just be a spectrum, and then you can truncate or take different loop space, and then you get a space. So it's kind of an enhancement or enrichment of the mapping space in the infinity category. And to talk about this, you need the K-linear structure. So this is by adjunction equivalent to morphisms from x to gf of y, which so this would be in D of A G. So this is the morphism object in the group quotient, and this is the morphism object in D of A. And so this is equivalent, we know gf of x. This is equivalent to the coproduct of g is in g of, let's say, morphism in D of A from g acting on x to y. So this is somehow why this adjunction is so helpful to have. Before, at least to me, there was no way to compute the homs, if you want, the morphisms, in the infinity categorical group quotient. And this proposition tells you that at least for those objects which come from objects in the original category, you can compute them in the way that you would expect them to do, which is exactly the same way that you would compute them in this Q group category. And this is also this equivalence that we now have at infinity categorically allows us to prove the main theorem. So let me proof sketch of a main theorem or main theorem. So step one is to say that you want to construct a functor from the infinity categorical group quotient to the derived category of this Q group algebra. You want to use the universal property, which means you just need a cocone under your diagram. So step one, you show that up to equivalence of DG categories. So you have to replace all of them by slightly different or equivalent, but not quasi-equivalent or really equivalent, really just equivalent DG categories can realize. We can realize this Q group DG category as a cocone under the functor from BG to DG cat, which maps the point to A. And then, step two says that use by the universal property of D of A, G, you get a, by the universal property, you obtain a functor, functor. So from D of A, G, let's call it U for universal, to D of A star G. And this functor actually lives under the cocone. It's a functor which extends to morphism between cocones. So in particular, we can put here D of A, and here we would have the functor f from just now. And here we would, because f was the functor from the cocone, and here we would have some different functor. Let's call it D of fa, with fa is the functor from A to A star G, it's the obvious inclusion. If you want for the group ring, this group algebra, this would be the inclusion of the identity component into the group ring. It's just the naive inclusion that you have of the original DG category in the skew group DG category, and it's not a fully faithful functor. It's just a basically Hom-wise inclusion, and we obtain this functor, and yeah, in such a commutative triangle. So step 3, we now check that U is fully faithful on the image of F. So we have, if we look at morphisms in D of A G from f of x, f of y, this gets mapped by U to morphisms in D of A star G from fa of x to fa of y, which, so we know how to compute the guy on the left. This was the proposition. This is the coproduct in of morphisms in D of A over G in G of mapped from G dot x to y. In this here, so this is equivalent to, first of all, it's we can look at the DG Hom in the DG category A star G from fa of x to fa of y. And by general results, when you passed from a DG category to its derived infinity category, this is exactly how you compute the morphism object. You compute it by, or it's equivalent to the DG categorical Hom. So this would be the DG Hom. And this is equivalent by the definition of this Q group DG category also to the coproduct of G and G, Hom DG in A of G dot x, comma y. And this is equivalent again to the coproduct over G and G of the morphisms in D of A from G dot x to y. And then you check. So you get a map here, and you check that this map has an equivalence. Check that this is an equivalence. And clearly there's a small thing to check there. It's not automatic, but at least we can see that both sides are equivalent to the same object. So they can be equivalent as well. And then step 4, you need to use one more result, basically, that we use that this infinity group quotient, D of AG and D of A star G, are generated. How do you spell generated? Generated by objects of the form you apply F to X, where X is in A. So if you look at the original DG category A, and you look at all the objects which this induces in the group quotients, these objects generate your group quotients. Clearly, the group quotient must be generated by where it comes from. And so, because the functor is fully faithful in generators, you can then show that it is fully faithful and essentially surjective. So this is the proof sketch. It's not a full proof. The details are in the paper, but this is the essential steps in the argument. And let me mention some consequences of this. So, consequences. Corollary, maybe first corollary. So the screw group algebra, it's an explicit construction or screw group DG category, which is nice. But now this this gives you now formal properties of this construction. For instance, you now know that the passage the passage to the skew group DG category commutes with homotopy colimits. Homotopy colimits of DG categories. And the way you prove that is to equivalently, instead of homotopy colimits, you could also say infinity colimits, and you just use that homotopy colimit or infinity colimits, homotopy colimits, commute with homotopy colimits. And so this is just a homotopy version of the result that, or infinity version of the result that colimits commute with colimits. And so, yeah, say if you're gluing categories along colimits, you can now commute this process with group quotients, which is one of the statements that I was very interested in having when I started this project. And then there's another equivalence. So if you look at the derived category of A star G, we know that this is equivalent to dAg. The colimit over Bg, so this is the colimit over Bg of d of A, but this is actually equivalent to also to the limit of Bg of d of A, which this fact follows from presentable left stable is equivalent to presentable right stable opposite. So this is some general duality for presentable categories, which allows you to prove such a statement. So you can compute the derived category of the skew group DG category also computes the limit over BG, which you could call the infinity equivariant objects. So this would be the infinity version of equivariant objects. And in particular, if we restrict to the heart, so now we can pass to homotopy passing to triangulated homotopy categories. Homotopy categories. These have T structures, and we can then restrict to the heart, and restricting to the abelian heart. We obtain an equivalence of abelian categories. Hearts, so the hearts of the standard T structures. We obtain an equivalence of one categories between the module category of, so let's say this is for the case that A is an algebra. A is just a K algebra on a DG category. Then modules over this Q group algebra, A star G, is equivalent to modules over A and then G equivariant. So there are things to check here somehow, that when you all do these infinity equivariant things, and then you pass to the homotopy category and the heart, that first of all, this equivalence of categories restricts to the heart, and then second of all, that the infinity equivariant guy gives you the classical equivariant guy. Those are two things you have to check. They're checked in the paper. But this gives you such an equivalence of categories. And what's interesting is that this is new. This equivalence is new if the characteristic of K divides the order of G. So it was known before in if you want in good characteristic, but in bad characteristic, the previous constructions of this equivalence, they wrote explicit formulas, and those formulas you just couldn't write down in the bad characteristic, and this proof somehow never really writes a formula. So it just works out by abstract reasons. Yeah, which I think is quite interesting. And then let me end with a comment on orbit categories. Orbit categories. So this corresponds to the case that G is equal to Z. And in this case, so a G action or a Z action is fully determined by some of the action of one, the action from A to A, and so I think the first reference on triangulated orbit categories is due to Keller. So we have Keller triangulated orbit categories. And then there's a more recent reference due to Leo Keller, sorry, Keller, Leo Chiu, where they also look at somehow these orbit categories, DG orbit categories. I mean, DG orbit categories were also defined in the original work of Keller. DG orbit Keller triangulating the DG orbit categories, but they look at DG orbit categories with respect to non-strict actions. Non-strict actions. So you would have, say, A is a DG category, and F would be a DG bimodule, DG mod A, and let's assume, I don't think they need that assumption, but we do, so or I do, assume F induces Morita equivalence, induces a Morita equivalence. Then you can check that somehow there's for this just having a bimodule, there's still a definition of orbit DG orbit category, and then the derived category of, I'm writing small again, yeah, notice at the end of the talk. Okay. A mod F, so this would be the DG orbit category. Orbit category, this would be equivalent to which is the this would be equivalent to the infinity categorical group quotient. So the colimit over Bz of you take B of A, where the action of one is mapped to the functor induced by F. And right, so this would be the orbit category. In the special case that the action is strict by a strictly invertible DG functor, you would recover the formula for the skew group DG category, but there's a more general construction for non-strict actions, and then you can still check that this computes the infinity categorical colimit. So yeah, this is all I wanted to tell you about. So thank you for listening, and
Thank you, Merlin. Let's all give the speaker a round of applause.
you too. Thank you. Thank you.
Okay, I think Bernard said in the chat that it's Keller.
Yeah, sorry,
Yes.
typo.
Any questions, anybody? So I quite like this corollary too that you have on the bottom left corner of the screen here. So, I mean, I don't know. I mean, I don't know if this question makes sense. Like, can one generalize this to group objects in some topoi, or are there some theoretic techniques that you're using here that can't be?
Oh yeah, I don't know about that at all. Somehow, how do I? I mean, so somehow the thing that is really, I don't know about module actions in the context of topoi. I don't know if this is documented anywhere or if it's expected or not, or if this does make sense for obvious reasons. Not something I've ever really thought about or but what's really important here is this technology of using modules and linear structures, this infinity module. And I mean, you can do all of these somehow very formal computations with them that just work out. And yeah, I haven't seen such a thing for topoi. I may just be ignorant, but yeah, that's some other thing I wouldn't know about.
And am I correct in understanding that this co-limit over PG of this dA is, that's not a very nasty thing to compute, I'm guessing, in practical examples?
I mean, you can compute it. I mean, the co-limit, like abstractly, the infinity categorical co-limit, I mean, it's just abstractly defined. Whenever you have these infinity categorical constructions, some of the question when you want to compute things, how do you do that? So, I mean, you can read the main theorem in two ways. One way would be to say that this abstract infinity categorical group quotient, you can compute it using this concrete construction of this Q group DG category. And vice versa, you can read it that this Q group DG category has the universal property that you would expect it to have.
Yeah.
And I think, I mean, either statement is not obvious, I think. I mean, maybe both are expected, but it's not, neither statement is obvious.
Okay, thank you. Any other questions, anybody?
Yeah, I have one.
Hey.
Yeah, go on.
Hi. Thanks for the talk. Do you have the reference for this thing about the module categories of the DG algebra that you have up there? That you need the invertibility of the characteristic of the G in the of the order of the group.
That you need this?
No, you say that
No,
the
for the
characteristic has
statement.
to
Oh
be
yeah.
prime to the order of the group, but I mean for rings, this you don't need this assumption, but for DG algebras apparently you do, right?
No, this is A is a K algebra. Let's say a ring. This is only for A.
Okay.
So you're saying it's in the literature. So I found it in my paper. I cite a place. I can look it up. Let me stop sharing for a second. Yeah, in my paper, I cite a place.
Yeah, but these are the ordinary categories of modules over the.
Yes. These are just the modules, yes.
Okay.
They're really the classical one categories, and I cite the paper by I cite three papers for this, three references I give. One is Elagin on equivariant triangulated categories. That's, I think, the first with a number. And well, no, I also cite Balmer. Well,
Okay.
yeah, it can also be deduced from a paper of Balmer, using another paper that I also cite.
Okay, it's in your.
So,
I will check it out. Yeah.
mhm.
And I have maybe one more comment.
Yeah,
Yeah,
please.
please.
You wrote down this adjunction GF at some point, and you said that the composition is this coproduct of the.
Yes.
Yeah. But usually when you want to prove things in the finite group equivariant setting, you say that this composition is a monad, and by
Mhm.
Balmer's result, you use the separability that maybe this composition is reduced by the forgetful and the induction factor that you have, right?
Yeah, exactly.
That the factor is separable. Do you have this thing in the infinity categorical setting, and do you need it at some point? Maybe.
Well, I mean, it does form a monad. You can formally you can deduce that. There's some infinity. Yeah, you get an infinity categorical monad. There's whenever you have an adjunction, the composition of the functors gives you a monad structure. You can remind me what separability statement is, what it means.
Yeah, it's I don't remember the definition right now, but you can find it in Balmer's. It has to do with I think you have a section on the home sets, right? I mean, the forgetful functor, your G, is separable if and only if the monad is separable. I think you have this statement in Balmer's results, if I'm not mistaken. And then if you have this separability thing, you can say that the equivariant category is the category of modules over this monad. So you can use this to prove a lot of results.
Oh yeah, this is also true infinity categorically, yes, just by the Babek-Louis theorem. I do mention that in the paper as well. So you do get a monadicity of the right adjoint.
Okay. And this is when you want to have the order of the group being comprimed to the characteristic. That's why you needed to. I mean, I think I remember that the separability has to do with these things, right? When you have a order of the group comprimed to the characteristic of the field, you have a separable monad, and you can prove things.
Okay.
But maybe
Well,
this is
the
the
monad still
difference in the...
exists otherwise, and I prove that at least the infinity adjunction is still monadic. So you still
Yeah,
have the theorem without the assumption of the characteristic.
okay.
Thank
Yeah,
you.
thanks.
Yeah, thank you for the question.
Any more questions? Well, if we don't have any more questions, let's thank our speaker one last time.
Thank you.
Okay, thank you all for coming. We have Michael Herbeck speaking next week. So hope to see you then. Bye-bye.
Bye.